A very good morning, doctor. I am VETRI from dt11. This is my mass balance and energy balance for the cpts. This is the question I generated for the EB and BCPTS mark percentage. A gas mixture containing 25% mole percentage of CO2 and 75 mole percentage H2 enters a absorption column at a flow rate of 150 kmol per hour. So the flow rate of the gas is given. The gas is treated with amine solvent to remove CO2. The pure DEA solvent enters at a flow rate of 180 kmol per hour and absorbs 85% of the CO2 from the inlet gas, which means the pure DEA, which doesn't uh, contain any water. So it's a 100% pure DEA. So we assume in this calculation the solvent is 100% pure DEA. The inlet gas and solvent enter the column at 40 Celsius and outlet solvent leaves at 52 Celsius. This information will be helpful for the enthalpy calculation and assume no losses of the amine solvent. Now let's look at the answers. This is a process flow diagram that I draw from the question. Here in the absorption column, there is two inlet and two outlet. The first inlet would be 180 kmol per hour of DEA, which is pure solvent, and the second inlet would be 150 kmol per hour of gas, which consists of 0.25 kmol mole percentage of carbon dioxide, whereas 0.75 mole percentage of hydrogen. Then the first outlet would be carbon dioxide and DEA. I mean the amine solvent which absorbs the carbon dioxide. All the amine solvent would be goes out in the stream 3, which is 180 kmol per hour, whereas the absorbed carbon dioxide will comes together in the stream 3 and the non-absorbed carbon dioxide will goes out at stream 4 together with the hydrogen. And in this process flow diagram, the assumptions that I assume is no reaction occurs, all hydrogen removes as gas, all DEA remain as liquid, no energy released to the environment. In inlet amine DEA is pure DEA. Now let's look at the degree of freedom analysis. For the DOF analysis, there are four unknowns, which is the mole fraction and also the molar flow rate of the gases. There is one overall mass balance and two information given, which is CO2 absorption rate and H2 went to stream 4, which means the all the H2 that inlet went to stream 4 and there is no mixture of H2 in stream 3. Then one CO2 balance, which the answer equal to 0 and it is solvable. And for the question C, which is calculate the unknown values and mass fraction of CO2 in the final solvent stream. So we have to calculate all the unknown values and also the mass fraction of CO2 in the final solvent stream. To solve the unknowns, first we will start from the 150 kmol per hour feed gas, which is the basis, and then CO2 is 25 percentage and H2 is 75 percentage in the feed gas. So if 0.25 times with 150, we will get 37.5 kmol per hour of CO2, whereas 0.75 times 150, which is 112.5 kmol per hour of H2. So we already found the inlet of CO2 and H2 to the absorption column, and we already have the DEA molar flow rate of the DEA to the absorption column. So now goes to the outlet. In stream 3, absorb CO2, which is 0.85, as the absorption column absorbs 85 percentage of CO2, 0.85 times with 37.5, which is inlet of CO2, and we will get 31.895 kmol per hour. So the N1 is equal to 31.895. The remaining CO2 will go to stream 4, which means 37.5 minus 31.8 equal to 5.6 to 5 kmol CO2 per hour. And then all the H2O will go to the outlet stream, which means the outlet H2O for stream 4 is 112.5 kmol per hour. Okay, we already got the molar flow rate of CO2 and H2 in stream 4. So we will add it up to calculate the total molar flow rate of that particular stream. So we got 118.125 kmol per hour in stream 4. So using that, we will calculate the mole fraction of it. So the mole fraction of CO2 we will divide the molar flow rate of CO2 in steam 4 over total molar flow rate of steam 4, and we got 0.0476 mole CO2 per mole. The same equation we used to calculate the mole fraction of H2, and we got 0.9524 mole H2 per mole. Then moving forward to the next part, in that question we also has been requested to calculate the mass flow rate or mass fraction of CO2 in DEA rich solvent. So to calculate it, uh, first we will convert the mole flow rate in steam 3 to mass flow rate. So we will times it with 44 kg per kmol, and we got 1407.25 kg per hour. Then we have to calculate the total mass flow rate of the steam. So we will add 1407.25 kg per hour with DA mass flow rate, which is 180 times with 180, which is molar flow rate of DEA in that steam in steam 3, multiply with 120, which is molar mass of DEA, and we got 2000 21,600. So we'll add up with the mass flow rate of CO2, and we got the total uh, mass flow rate of steam 3 as 23,002.5. Then we will calculate the mass fraction of CO2 in steam 3, which is 1402.5 divided by 23,002.5, which is equal to 0.061 kg CO2 per kg. So we already answered all the questions they have asked in C. Now let's look at question D, which is calculate the heat duty required for the adsorption process, assuming the heat capacity of CO2 rich amine solvent, which is 3.8 kj per kg dot K, and the amine solvent molecular weight is 120 g per mole. To solve this, first we have to calculate the temperature difference. The temperature out minus temperature in, which is 52 minus 40, which is equal to 12 Celsius. Then we will insert those values into Q equation, which is Q equal to MCP delta T. M already given. I mean, we have already calculated the M, which is 21,600, and CP already given in the question, which is 3.8, and delta T we have calculated just now, which is 12, and we multiply all these, and we got the value. And after getting the value, we have to divide it by 3600 to convert it to kW. So the answer we got for Q is 273.6. That's all. Thank you.